Hi, so we are going to do just a quick review of a binary search tree, which will also serve as a motivation for our next topics. And since you are all binary search tree experts by now, so let's start with an exercise. So let's try to create a binary search tree and insert these numbers in the binary search tree. And then we look at what is the time complexity if we want to look up a number in this binary search tree. So here is what I ended up with when I did this exercise. So, and if, as you can kind of see, it's not a perfectly balanced binary search tree, but it's pretty good, right? Most nodes has a left and right child. So the time complexity of searching for any number in this tree is, like we learned previously, is proportional to the height of the tree, which is proportional to the log of n. So this is good because we can find a number very quickly relative to the number of nodes in the tree. So the next exercise, what about this sequence of number? If you insert these into binary search tree, what does it look like? So give this a try. Okay, so this is the binary search tree that you would end up with if you insert sorted numbers, right? It would basically just create a very, very imbalanced binary search tree. It looks almost pretty much like a linked list. So the time complexity, if we want to look up any numbers in this binary search tree / linked list, is proportional to the number of nodes. So this is terrible, right? So the moral of the lesson is basically we knew this from before, that the big goal of all these operations, search, insertion, and removal in a binary search tree kind of depends on how balanced the tree is. So on average, or in a good case, it should be log of n, but in the worst case, it will be proportional to n. Now, we want to avoid n as much as we can because the reason we want a binary search tree is to have log of n, right, rather than linear. So basically, we want a balanced binary search tree. And when how do we achieve that? Well, we usually achieve that during when the tree changes, and the tree change when we insert something or remove something, usually, right? That's not always the case. We'll learn a different tree that actually doesn't necessarily do that. But most of the time, when we insert or remove something in the tree, we change how the tree is structured. And we will, in that process, force the tree to satisfy some sort of invariant to keep it more or less balanced. And so here are some of the so-called self-balancing trees. AVL tree, which is what we're going to study, both how it works and how we'll actually implement it. We'll talk about Splay tree as well. There are other self-balancing trees, such as red, black trees, B trees, etc. We won't have time to get to all of them.